jeden.
Okay.
Nevím, jak to mám vymezit.
Nevím, tam to ok. Podejde to ok.
Ještě jeden dám, ano.
Tak, výborně. A ještě...
Dobrý, už je to pryč.
Okay, so good afternoon, ladies and gentlemen. So I have a big pleasure to introduce my colleague, but anyway, let me say a few words about him. So he did his PhD thesis under the leadership of Milan Pokorny, which means hard time for him because Milan is very precise, but very nice guy. Then he moved to institute. And another hard time, but anyway, we sent him to Switzerland, and he spent a nice time with Professor Delelli. So he learned a very nice part of, let's say, mathematical analysis. This convex integration. Sorry. And this was really crucial because this was like a big step in Euler equation and let's say answering concerning uniqueness and Ondřej with Elisabetta Cudaroli and Delelis, they had very important paper concerning Euler equation and compressible case. And today he will speak about another problem, which is maybe also interesting. This is up to you, and it is about time periodic solution and construction interactions. Please.
Okay, thank you for the very nice introduction and for the invitation to have a talk at this seminar. So you don't have to worry. Today there will be nothing about convex integration and stuff and so on. So this is more in the area of research of Šárka. And also this is a joint work with her together with Vašek Mácha from our institute and together with Srdjan Trifunovic from the University of Novi Sad. So if you take a look at the title of my talk, there are three key components to the problem I want to study. So first of all, there is this time periodicity. So we look for time periodic solutions to some problem. And the problem consists of interaction between a fluid and some solid. So the interaction problem is the second main component. And the third component is the fact that the fluid is compressible, which presents some further complications. Okay, so when you take just two of these three components, there have been some previous works. Of course, the list which I present here is not exhausting. I mean, there were plenty of other works in this area, so I listed just the most If you forget about any interaction between fluids and solids and take just time periodic weak solutions for compressible fluids, and that's it. So you have the time periodicity and compressible fluids. There have been two important papers concerning existence of time periodic weak solutions. The first one was for the barotropy case, which was done by Eduard, Šárka, Anna Pesotova, and Ivan Straškaba, all of them from the Institute of Mathematics of Czech Academy of Sciences. And later on, for the full system with temperature, and with the result was proved by Eduard, Piotr Mucha, Antonín Novotný, and Milan Pokorný. Okay. So now let's forget about time periodicity and take weak solutions for interaction problems between compressible fluids and some kind of elastic structures. So this is sort of a recent topic, and the important works here were done by Dominic Bright and Sebastian Schwarzacher in 2018 for something which is called Coiter shell, but I will not go into details very much about what this means. And for thermoelastic shells, so with some kind of temperature dependence as well, this was done by Srdjan Trifunovic and Wang in 2023. And finally, if you want to take a look at time periodic interaction problems, the only results up to now were done for incompressible fluids. So this is in the 2D case by Casanova, and for 3D fluids and the existence of weak solutions, there is a couple of papers by Claudio Mindrila and Sebastian Schwarzacher from recent years. Okay, so our aim is now to combine all three of these components, so to prove existence of weak solutions to time periodic problem of interaction between compressible fluid and some kind of elastic structure. So let's take a look in more detail at what we are studying. So we were able to show something, but there have been several constraints which are sort of not optimal, and we would like to maybe in the future make them better. So, but so far we have only this. So first of all, our problem is two-dimensional. So the fluid fills a two-dimensional domain, which is denoted by omega. And for technical reasons, this domain is actually a rectangular domain, and we impose not only time periodicity but also periodicity in both spatial directions. Right? So we have a rectangular domain filled with fluid, and inside this fluid there is a beam which is supposed to be viscoelastic. I will show what it means for the equations a little bit later on. And so what is somehow crucial here is the periodicity in the vertical direction. So in order to prevent any kind of contact problems between the beam and some sort of boundary, we simply prescribe that the problem is periodic in z direction, which then implies that there a priori cannot be any problems with the beam touching any kind of boundary. So concerning the notation, we will use this gamma for the interval 0L. Gamma t will be the space-time cylinder related to gamma. Omega, as I told you, is a rectangular domain, so it's 0L in the horizontal direction and minus HH in the vertical direction. So this is the domain which is filled with the compressible fluid. The space-time cylinder for the fluid is denoted by Qt. So our variables are time, which is denoted by t, and horizontal variable is denoted by x, vertical variable is denoted by z. So eta of t and x denotes the vertical displacement of the beam. So you will notice that the beam can only displace in the vertical direction and not in any other direction. So the beam is really described by a function of the variable x, which of course at different times can take different values, but still. One of the problems also which we have is that this displacement a priori does not necessarily need to be inside of the periodic box. So it can travel outside of the box, but since the problem is periodic, it will then appear from the bottom. I will show you a picture a little bit later on. So this eta hat denotes this function, which is restricted to have values in the box minus HH. Okay, so the position of the beam is denoted by gamma eta here. So this is just a couple of x and the value of eta t and x. And finally, what we use is rho and u for the density and the velocity of the fluid. And I will get to the equations later, but here is the picture to have in mind, right? So this is our periodic box. It has a length L and a height 2h. And optimally, the beam should look like this. It's like inside of the box, but It may happen that it travels outside of the box, and if it travels outside, so for example here, it appears at the bottom like this. Then when it goes back, then it appears right here again, and so on. So this provides a graph of this eta hat, which relates to eta, which is here with the dashed line. Okay, so what are our equations? So it is easier. So we have simply compressible Navier-Stokes equations on the fluid domain, which we don't denote by Qt. The view here, and I believe all of you know this system. Is and the stress tensor here is in the following form. So it is mu times this tensor here, and zeta times divergence of u times identity. So here mu is the shear viscosity, and zeta is the bulk viscosity, and both of these parameters are assumed to be larger than 0. Side we have time periodic force F, which acts fluid coupled with the equations for the beam. So the displacement of the beam is denoted by eta, and we have this the behavior of the viscoelastic beam. So the elasticity is related to this fourth derivative of eta here, and the fact that the beam is viscoelastic is represented by this term here, eta txx. So all these terms help us later on in the estimates. And on the right-hand side of the force, and then there is this coupling term. So this is a term which acts on the beam by so which this describes on the beam. And again, I will come later on what this really means. Here, this F fluid, and also this S eta, which appears here, is simply related to the fact that this formula, this equation, is sort of stated in the Lagrangian coordinates, whereas this fluid equations are described by fluid coordinates, and there has to be some sort of term which relates these two coordinate systems. So for technical reasons, this S eta appears here as well. Okay, and now the equations. So there are two coupling. The kinematic coupling is simply the fact that the trace of the velocity on the beam is equal to the displacement of the beam. So sort of to the velocity of the displacement. So eta t times E2. So this also means that the beam can only move up and down. So the velocity here, the trace on the beam is a vector by which the fluid acts on the beam is simply the jump across the beam. So basically, the difference between the value at the bottom and the value at the top of the beam. So this is here. So minus pressure times identity plus the stress tensor. Good. So moving further, so we have almost everything, but we don't have the boundary conditions. But as I said, we assume that the boundary conditions are such that the problem is periodic in all directions. So eta, the displacement, is periodic in the x direction, and the fluid is periodic in x and z directions. And moreover, the problem sort of uniquely, we fix to 0 or equivalently x equals to L, and we fix that eta at the value of the displacement at point 0 is equal to 0. So we simply prevent the whole thing to just move up and down arbitrarily, which will bring some sort of non-uniqueness to the system. So this helps us a little bit to formulate a problem which sort of makes sense in time periodic solutions. Okay, so now you may say, okay, this is not really very nicely or physically reasonable problem, which I would agree with you. But from the mathematical point of view, even with this sort of non-physical boundary conditions, the problem is challenging enough, and it took us some time to figure out how to prove existence. But of course, for the future, which I will mention at the end of my talk, there are ways how to proceed and problems to solve in order to make this maybe more physically reasonable. Okay, so the good news is for our mathematical analysis is that the nature of the studied problem enables us to work with two equivalent formulations of the problem. So either you can work with what I already described, but also you can look at it in a different way, and you can look at the problem as a problem on a moving domain where eta represents the lower and upper boundary. So the picture is like this. So you can either look at the problem like this. So you have a periodic box, which is inside is a fluid, and inside of the fluid there is this viscoelastic beam, which maybe this may disappear here and appear from the bottom and so on. But this is one the problem like this. So here you have, of course, moving domain which remain fixed, but then again you have the fluid really inside between these two interfaces, sort of. And bottom and at the top is the same. Like forcefully is the same. Right? So yeah, so here is just the notation that omega eta and q eta represents the moving domain frame, whereas omega and q represents the fixed periodic box. So this is related to, so omega eta and q eta is related to this picture, whereas omega and q is related to this picture. Okay, so finally I'm getting into the definition of solutions which we look for. So you may simply ignore all these hashtags here because this just represents the fact that the functions are periodic. So as I said, the program is periodic in all directions. So everywhere, every function space has this hashtag. But otherwise, the function spaces are basically what you would expect to have. So for the density, you have L infinity L gamma. I recall that this gamma is the same gamma which appears in the pressure law. Our pressure is assumed to be rho to the power gamma. The velocity is in L2H1, and the displacement itself is in L infinity H2, which again is somehow related to the fourth derivative which we have in the system in the space H1, and also in this its time derivative is in L infinity L. So this all these terms, basically all these function spaces, are naturally related to the program, and you will see them also arising from the energy inequality, which I will present a little bit later. So of course, the kinematic coupling, so the fact that the trace of U at the beam, so we use this this operator gamma to denote the trace of U at this this eta is equal to eta t. So this this holds on gamma t almost everywhere. Then we have the renormalized continuity equation. So this is standard stuff in compressible fluids. So we have formulated in this way. So here, if the of the continuity equation, but we also assume that the continuity equation is satisfied in this sense for some functions b, small b and capital B here. So this is pretty much standard in compressible fluids. And finally, the most important term is the coupled momentum equation. So what happens here is that we have just one equation out of the two equations in the strong formulation of the system. So how this appears is pretty much natural. So you take the strong formulation of the fluid fluids, the momentum equation of the Navier-Stokes system. You test it by a test function and you integrate by parts. And when you integrate by parts, especially here in the pressure and in the stress tensor, you will see that a term which is exactly the jump on the beam, when I go a little bit later, a little bit before. So exactly when you integrate by parts, this kind of term and that's the reason why you have just one equation here. You have the terms here. So basically, on the left-hand side, it's together, and other forces. So one force is coming from the beam equation, and the other force is coming from the fluid equation. So here, of course, the test functions phi and psi cannot be really arbitrary because the equation was born out of the fact that the trace of pi on the beam was equal to psi. So this has to be preserved. So here, this is satisfied for all test functions, phi and psi, having this crucial property that the trace of pi on the beam is equal to psi times, of course, the vector. This is basically the weak formulation which we want to prove. And our main theorem finally is given data of the problem. So capital H. What is this sort of a parameter which also has to be prescribed? So the mass of the fluid is prescribed, and gamma is a given parameter. And then for external forces in suitable spaces, so for for technical reasons. So having this data, we claim that there exists at least one time periodic solution satisfying the property, such that all the facts in the definitions are satisfied. So mainly the equations, and also the energy inequality is satisfied. So the energy inequality on the whole time interval is simply just this. So you don't see any energy at time t and energy at time 0, because both of them are equal to each other and they cancel. So the only thing what remains are the dissipative terms. So we have one dissipative term from the machine. And this also tells you why it's important that we have viscoelastic beam and not just elastic beam, because we would not have any kind of information here. So this is really important term for us. And on the right hand side we have the forces. So terms with the forces. So this energy inequality is satisfied, and also we have that the supremum of the energy of the system plus the dissipative terms are bounded of the problem. So if you take a look at the energy, which you don't see here, but we will work with the energy excessively. So there are terms which are natural, right? So you have the kinetic energy of the fluid. You have this term which comes from the pressure, so it's like the internal. And you have terms eta tt, so integrating by parts gives you 1/2 eta t squared here, and the fourth derivative for spatial derivative is appears under the time derivative when you derive it, so therefore there is the supremum of this term, and these two terms are the same as here above. Okay, so this is what we aim to prove. Now the question is how to do it, right? So the proof will be sort of, or my presentation will be from now on split into two main. The a priori estimates are derived, and most importantly, how we are able to show, assuming that we have a solution smooth enough, that the energy of the supremum of the energy over the time interval is bounded. Right? Try to prove existence of something. You want to work with some sort of a priori estimates. In time periodic problems, this to show this property is maybe a little bit difficult than without than in classical initial value problems. So my talk on this property, and in the second part, then I will say some words about how we construct an approximate system in order to pass to several limits. And so maybe the more interesting part is really how to get this property here, right? Because what you usually want to do is just test the coupled momentum equation by u and eta t, which are sort of natural test functions, right, in order to derive something about the energy. But since you are working with the time periodic problem and you integrate it over the time interval 0 capital T, everything what is under the time derivative simply disappears, and you have only this. If you have smooth solutions, then this is equality now and not really inequality. But you want to deduce something for this functions u and eta, which appear on the left. Really easy, right? Because on the left-hand side, as I said, you have something for u and you have something for eta, but there is nothing for rho. Whereas on the right-hand side, you have rho here. So this cannot be enough to deduce any kind of information, right? Unless, of course, you are able to estimate rho in L1 and use just the mass, but this is not really possible. Assume in infinity, and you don't have this W12 norm of gradient u, which is in here, is embedded into any LQ, but not really L infinity. So therefore, you have to estimate rho in some L infinity LP space with some small p, but you don't know you don't know that this is bounded. So you arbitrarily large and P, which can be arbitrarily close to 1, and estimate this term here like this, and then you do a little bit of work to estimate U in L2, L3 by the left-hand side here by this term, which combining a Korn's inequality and a Poincare inequality to do it, right? And you can end up with the estimate like this, that this term which appears here on the right-hand side is bounded by this guy, and also this guy, but this guy appears here anyway, so this is not really harmful in any way. This is okay. That's the question, right? And to use something which we don't know already. So we simply say, okay, P is sufficiently small, sufficiently close to 1. And in the future, we would like to have the density to be estimated in L infinity L gamma for some given gamma. And this is hidden in the supremum of the energy. So this to some, but as far as things stand at this moment, we don't know that this is bounded. Okay, so in the end, we end up in the first step by this estimate, right? So we have U in L2 L8 and eta supremum of the energy over the time interval to some power kappa, which in the end will be quite small. Okay, but now we have to go further. And here comes the key step, which is probably similar to all time periodic problems. How to deduce something for the supremum of the energy. And what we do is, we do basically the same thing, but we don't integrate over the whole interval, so 2 time instance S and T. And if you do that, you really have on the side energy at times S. And these two do not cancel at this point because T and S are just some random points in the time interval. And then you have again the right-hand side, which is the same, but there can be bounded by the integral of the energy between these time instance S and T. Now this guy is the integral of a positive function, right? And the energy is positive, so therefore this can be bounded by the integral over the whole time period of the same guy. And now we do some tricks with the mean value theorem. So basically, we find out that there has to be a time instant where E, the energy evaluated at this time instant, is the average of E of this integral. So basically 1 over capital T times this integral. And if you plug S equals to this time instant and then take supremum over T here, you end up basically that the supremum of the energy is bounded by this guy. This is the first crucial step, right? So we have the supremum energy bounded by the integral of the energy. And now what we want to do next in order to close the circle is to figure out the opposite. So we want to have that the integral of the energy is bounded by a sufficiently small constant times the supremum of the energy, plus maybe a large constant here. And if we do it with this delta zero being sufficiently small with respect to this supremum of the energy is bounded. So this is the idea how to proceed, right? So we have, I will go back, we have that these two guys are bounded by the constant times the supremum of the energy to some power. that the supremum of the energy is bounded, and also, of course, these guys are bounded. Okay, so this is sort of important, but maybe not that involved step in order to the estimate for again by means of the supremum of the energy to some power, and as it turns out, the power is 3 times kappa if the kappa is the estimate. Comes lies in density term. So we need to use the Bogovsky operator in a sort of clever way to deduce an estimate like this. So I state here simply just the end product after all the estimates with the Bogovsky operator, and you can indeed show that the integral of rho to the power gamma is bound. It's very close to 1, but it's smaller than 1, and this is crucial. Because if this power would be equal to 1, it would not work. But luckily, this power can be shown to be smaller than 1, and therefore you can use this estimate in order to show that the integral of the energy is bounded by this. And using the Young inequality here on the supremum of the energy, you can bound it by a sufficiently small constant times the supremum of the energy to power 1, plus maybe a large constant, but a fixed constant here. And therefore, you can close the circle and show that the supremum of the energy is bounded using this series of estimates here. So I would emphasize that the important work really here is hidden, and I will not be talking about details how to get this, because this is technically quite difficult, but in the end we are able to show that it really works. So what is in here is, and you maybe not see it, is that the supremum of the energy. This is the closer of the first part of the proof, that for sufficiently smooth solutions, you can show that the supremum of the energy is bounded. And now you would like to take this information and construct some sort of approximative scheme such that when you pass it, you recover. And this can be done by a 4-level approximation scheme. So first of all, we introduce finite dimensional spaces in time and space variables. So we work with finitely dimensional spaces in time and space variables together, that these finite dimensions are the same in the time and space variables. However, in our case, this cannot be. This is not possible. I will try to explain why it's not possible. So you have to have separate basis for this time variable and separate basis for space variables, and you have to first pass in the limit in one of them, and only then pass to the limit in the other one. Then in the approximation scheme, we decouple the problem. So we sort of solve separately the fluid equation and separately the beam equation. And we introduce a penalization term where penalization parameter epsilon appears here, which when you pass with epsilon to 0, it sort of forces the trace of the velocity to be equal to this eta t. So in the approximative scheme, terms like this will appear both in the fluid equations. I think this term appears in the structure equation, and in the fluid equation you have similar term as well. Okay, and then we do usual stuff from the theory of compressible fluids, from the theory of weak solutions to compressible fluids. So we introduce artificial diffusion in the continuity equation, and as it turns out, you can the diffusion parameter can also be epsilon, the same one as is here in the panelization. We introduce artificial pressure as well, so this term delta rho to the power A for some large A, for technical reasons again. And then some other helpful terms multiplied by delta appear in the fluid momentum equation as well, which provides some additional regularity at the first approximation levels, but then they disappear. Then they disappear when you pass with delta to 0. So this is the idea somehow. I will not really show you the approximative scheme because it's quite complicated. What I will show you is the order in which you pass to the limits. So first of all, you pass with time basis m to infinity, and only then you are able to pass with space basis n to infinity. In the third step, you pass with epsilon to 0. You couple back the separated equations when you do this this limit. And finally, you make the last limit delta equals to delta goes to 0. So some more words about why we are doing it this way. So the reason is the following: in the first limit, when you pass with m going to bounded by constant. And why is that? So this estimate, if you remember, and I will go back to the crucial point, which was here, is that we took the test function multiplied sort of by the characteristic characteristic function of time interval st for arbitrarily as nt. However, the characteristic function of such interval is not really cannot be expressed by a finite number of basis functions in time, right? So this step you cannot do unless you already passed with m to infinity, and you have infinitely dimensional spaces in time variable. So unless you pass with m to infinity, that the supremum of the energy is bounded. So you may ask yourself, what information do we have? Because here at this level we didn't have anything, right? We have just this, but here there was supremum of the energy. However, here we take advantage of the fact that we have some other terms in the equations in part A appearing here, and we have also the artificial diffusion in the continuity equation, and these two things together provide you with the estimate of rho in LA on spacetime. This estimate disappears once you pass with epsilon. And then you have this information, and therefore you are able to deduce from what you have all these kinds of estimates. Notice is that none of them have infinity time come from the fact that the supremum of the energy is bounded. And this is not what you have when you start with. But you have information which arise from the approximation. So in particular, there is this term which is sort of artificially included in the approximation scheme, and which does not appear in the original system. But you have also the first and the third information which comes simply from the terms which survive until you pass with everything to 0, right? So you can deduce all of these terms, all of these estimates, and all of them combined are sufficient enough in order to pass with m to infinity. Once you pass with m to infinity and you have now infinitely dimensional space in time, You can do this trick with taking the characteristic function of time interval S and T to deduce the estimate that the supremum of the energy is bounded by a constant. So you additionally have these kinds of estimates, and all of them, as you can see, have R infinity in time. So all of them arise from the fact that the supremum of the energy is bounded. So to conclude, you pass with M to infinity. Only after that you recover these estimates, and these estimates you need in order to pass with the space dimension to infinity. So you pass with the space dimension to infinity, and then it's sort of a standard way how to proceed further. So we need to deduce a priori estimates independent of epsilon, and then later on also independent of delta. But here we basically follow the procedure which we have earlier, right? And there are only few additional technicalities which you have to deal with, but nothing really crucial. So here you really deduce these a priori estimates independent of epsilon. You couple back these separated equations, so you basically sum the equations up. You pass to the limit, and in order to pass to the limit, you also need additional information which was not used before in the a priori estimates, but which can be indeed deduced, which is this estimate, basically additional regularity in space of this displacement eta. So this is something which follows the ideas of Muhaj and Schwarzacher. Because if you don't have this information, you are not able to pass to the limit in the energy inequality, if I remember correctly. So this is indeed something which we use. And finally, you pass with epsilon to 0. You deduce estimates independent of delta, and you pass with delta to 0. And this is sort of I would say the theory of compressible fluids, and there is really no significant difficulties related here to the fact that you are working with an interaction problem where you have beams and or beam and a fluid interacting together. Okay, so I'm almost at the end of my talk, so just some ideas how to proceed further with this problem. So of course, as I mentioned, what would be really nice is to have better boundary conditions. In particular, so the first step would be to have Dirichlet boundary conditions for the velocity on the lateral boundary. Of course, it's difficult to examine the problem without the periodicity in the vertical direction, because then you run into danger that the beam touches the boundary, which you would have to prevent. So this, of course, maybe also can be a problem to study, but if ever it is possible, that only under some smallest assumptions, which would prevent the beam to really touch the boundary. But the first problem with Dirichlet boundary conditions for you on the lateral boundary maybe should be possible. We have some problems with the Bogorsky operator there, so we decided to use the periodic boundary conditions also in the x direction as well. So these are two further generalizations, and of course, what would be interesting is to have a 3D problem. So here, I just mentioned is that if a similar construction would work, it would probably have to be only for very large gammas. So here in our the gamma was a parameter, and once we have fixed gamma, we can work with this p, which was like a parameter which was very close to 1, and so on. So if we would have a 3D problem, we would not only have gamma larger than 3 halves, which would it would have to be gamma larger quite a bit. So this is something which we would like to take a look at in future months and see whether it would work or not. Okay, and that's the end of my.